You heard a lot about random matrix theory and some semi-classical approaches, and today I will give some examples of systems which we use to test like Boegas-Giannoni-Schmidt conjecture. These are, you use systems, you compute eigenvalues, and then you compare statistics with predictions from random matrix theory. So in the first part, I will speak about the so-called billiards, and in the second part, I will briefly introduce quantum graphs. This is another type of system which is used to study aspects of quantum chaos. So here I will also explain how we use microwave billiards to get eigenvalues and wave functions experimentally. For this, you can use such microwave billiards. So first of all, just to remind you, what is a billiard? A billiard is a bounded two-dimensional region. Inside the billiard, the particle moves freely, and on impact with the boundary, it's reflected according to the rules of mirror reflection. And they are used as systems to study quantum chaos because you only need to change the boundary of the billiard to get chaotic dynamics or something in between. Today I will show some examples which do not comply with Boegas, Giannoni, and Schmidt, and these are all obtained with such systems. So, and as I mentioned, I was working in Darmstadt for 15 years. It's an experimental group. I was there as a theoretician, and they did experiments with so-called microwave billiards. These are flat microwave cavities, resonators, and you can use them to get the eigenvalues and eigenfunctions of a quantum billiard of corresponding phase. So first of all, what was a quantum billiard? Yesterday I mentioned it already. To get the eigenvalues of a quantum billiard, you have to solve the free space Schrödinger equation. So you can use any expansion in terms of plane waves. And then you have to choose a combination of plane waves which obeys boundary conditions, Dirichlet boundary conditions in this case. So at the wall, it should be equal to 0. This simulates a quantum particle which is trapped in an infinitely high well, therefore Dirichlet boundary conditions. And the eigenvalues and eigenfunctions are obtained by solving this eigenvalue problem. And when you do experiments with a microwave billiard, so there's a certain frequency below which the electric field of the microwave is perpendicular to the top and bottom. And there the Helmholtz equation, which usually is a three-dimensional one, is only two-dimensional. So this is the Helmholtz equation below this critical frequency where the electric field is perpendicular to the top and bottom. There you have a scalar Helmholtz equation, and the shape of the equation is exactly the same as of the Schrödinger equation of the corresponding quantum billiard. That is, you also have these boundary conditions. These come from the boundary conditions for electromagnetic waves in a resonator with a metallic wall. And if the metallic wall solves perfect electric boundary conditions, then you have exactly the same boundary condition as in a quantum billiard. So this was introduced like 30 years ago. There's a book by Stöckmann. I didn't mention it. It's called Quantum Chaos, and there you can find a lot of information on experiments with microwave billiards. So there was a group in Darmstadt. We did experiments with superconducting microwave billiards, which have an extremely high quality factor, so you can get all eigenvalues and eigenfunctions. I will show now. And there are also experiments with room temperature experiments with normal conducting ones, and these were done in the group of Stöckmann and Marburg. So how do we get the eigenvalues? You use a microwave resonator, you attach antennas. So you send in microwaves via one antenna, you receive it either at the same antenna or another one, and then you get the scattering matrix corresponding to the scattering process. And the absolute value square of this scattering matrix is equal to the microwave power coupled out divided by the microwave power coupled in. Now, if you plot this quantity versus frequency, then you get, in case where you have a superconducting resonator, very well isolated resonances, like these are all peaks. They are not overlapping because we have a very high quality factor in these superconducting ones. And the positions of these resonances, they yield the eigenvalues of the corresponding quantum billiard. So we use such systems to get up to like 2,000 eigenvalues. I mean, when this was done, it was in the 90s, there were no computers, so it was really, for them, for example, with the stadium billiard, we computed this few hundred, and they made one measurement and received 1,600 eigenvalues. So it was, and so this is a microwave billiard, and I will talk more about this tomorrow in the colloquium talk. So I just wanted to introduce them here, and I will talk in more detail tomorrow. So, and as I mentioned before, you can do any spectral statistics. Before you can compare to random matrix theory, you have to make sure that all system-specific properties are extracted. I mean, this Bregas-Giannoni-Schmidt conjecture, it makes predictions on universal properties, so properties which all the systems have. So the spectral density is a non-universal property, so you have to make sure that you unfold your eigenvalues such that they all have a uniform spectral density, which is a constant. And this is done by unfolding. I mentioned it, and Thomas Guer also mentioned it. To get this unfolding, what you do, you count the number of eigenvalues below a given E, and then you plot it. You will get a staircase function, and then you can, to get the smooth part, you can fit some polynomial. In case of a quantum billiard, it's very simple. So there you can fit a polynomial to the staircase function, and then you get then you can separate the integrated spectral density, which is just the integral over spectral density from 0 to E, into a smooth part and a fluctuating part. So this quantity is directly accessible because you only need to count the number of eigenvalues below energy E. So it's very simple to obtain. And the next problem usually is to find the smooth path of the spectral density, because then the unfolding is done by simply replacing the eigenvalues by the smooth part evaluated at the eigenvalues. Then you have unfolded eigenvalues, and to get this, you have to know the smooth part. You have to determine the smooth part. And for example, if you do it in a nucleus, it can be very difficult because there's no analytic result, so you don't really know what to fit to it. Usually you can fit some empirical formula, which is an exponential in square root of E. And microwave billiards and quantum billiards, there you know exactly what the smooth part looks like. It's just Weil's formula. These all, I mean, Weil he derived, Weil and also Ballion, they derived analytical results for resonators, two-dimensional ones, three-dimensional ones, of all different types. So when you have a two-dimensional quantum billiard, then it's given by a polynomial of second order in wave numbers. So k square is equal to E, and wave numbers just, we use usually wave numbers. I mean, I showed to you the relation between frequency and wave numbers. So if you have a frequent microwave billiard, there you measure frequencies, and to get the wave numbers, you have to take 2 pi multiplied with frequency divided by the velocity of light in vacuum, because this is done in, the experiments are done in vacuum. And here we use, I mean, in the numerical computations, I use wave number k. And then you have a polynomial of second order. This A is the area of your billiard. U is the circumference. So you can either use this formula to get to unfold, or but one usually does, one fits a second order polynomial to the experimental one or numerical one. And then if it doesn't have, if the fit doesn't yield these coefficients, then you know that you didn't get all eigenvalues. Or sometimes it can happen that you find too many eigenvalues because you misinterpret some, if you have numerical errors, or if you have an experiment, sometimes it's difficult to say whether a resonance is a resonance or just an artifact. But this is a very good way to find out whether all eigenvalues are reliable by simply fitting to such a polynomial and then checking the values of A and U. And usually one also looks then at the fluctuating part, because it should fluctuate around 0. And if it doesn't fluctuate around 0, then you know that there's something wrong with the unfolding procedure. And if you know that it's a quantum billiard, if you know that it should be a second-order polynomial, then you might have some mistakes in your numerical calculations or experimental data usually. But that's a very good procedure to find out whether you found everything and whether it's all not spurious eigenvalues or, but real eigenvalues. So now, before you can do comparison with random matrix theory, you have to make sure, there are several points you have to make sure that you fulfill them. One is the completeness of the level sequences. When you compare with random matrix theory, then you have to make sure that you have a complete sequence of eigenvalues, that there are no eigenvalues missing. I mean, I don't have time to talk about missing level statistics, but if there are eigenvalues missing, then you will immediately see deviations from random matrix theory. So, I mean, we have several works on that, but I don't have time to talk about it. But if you see deviations, so you never know whether it's incompleteness, whether there are symmetries which you didn't find, whether there are some non-universal contributions. I will give some examples. And so the first thing, you have to make sure that the spectrum is complete so that you can make any reliable predictions about your results or statements about your results. And also another problem, and Thomas already mentioned it yesterday, you have to make sure that you first separate by symmetries. If you don't separate by symmetries, then you won't find random matrix predictions for one chaotic system, but a superposition of several ones. And if you have too many symmetries, then, as I will show soon, you will find not GOE statistics in the time reverses invariant system, but Poissonian. And this I will give an example. So your first thing is you have to make sure that the sequence is complete. Second thing is you have to make sure that you took into account all symmetries. And if you want, you can also just leave it as it is, but then you have to compare to the correct random matrix ensembles. And yeah, and another thing is that, I mean, one of you yesterday already asked, I mean, before you can get reliable statistical results, you need a sufficient number of eigenvalues. So one possibility is that you have, for example, if you have a quantum billiard, do numerical computations, you have to make sure that you find at least like 200 eigenvalues. I think 200 is already sufficient to get some estimate on the properties, but usually it's better to have the more the better. Or if you don't have sufficient, I mean, if you just have a sequence of 200 eigenvalues, then it would be good to create an ensemble of systems. So usually when you have a quantum billiard, you can introduce some parameter, you can change it, and then you can get sequences of like 200 levels for different measurements, and then you can put them together if you are sure that the spectral properties should be the same for each member of this ensemble, and then do ensemble averages. And that's exactly what they do in nuclei. I mean, in this nuclear data ensemble, they used a very large number of nuclei. They had sequences from 5 to maybe 30 levels only. But when you now take an ensemble, these were like 1,000 levels in total, then you can get a very good, I mean, reliable results, statistically relevant results. So that's the next one. And so I will now show one example from nuclear physics. I mean, this is lead 208. They were able to find 151 levels. This is a lot for a nucleus. So they found 151 levels below a certain excitation energy. And then what is even more important is they were able to separate them by symmetries. I mean, in this case, one symmetry is parity. So this is parity. Another symmetry is angular momentum J, the total angular momentum. And they were able to separate by this. So they gave me these sequences of levels. You can see some have just 2, like that one, and this one has only 2. So these I ignored. And I required that at least 5, that the sequence should have at least 5 levels, and this is fulfilled for all the sequences in between. So I use these data and analyze the spectral properties. This is possible because you can take ensemble averages. But you first need to make sure that you separate by symmetry. So when you, for example, here I show just the fluctuating part, which I obtained by simply taking all 151 levels, and it fluctuates around 0, and this tells us that all eigenvalues were found. Now, if you do spectral statistics and take all of the eigenvalues irrespective of their symmetry, then what you obtain is nothing that looks like GOE. I mean, in this nucleus, you would expect some complex dynamics, that is GOE agreement, but here then you find Poisson. So if you don't care about symmetries and just put together all the eigenvalues and to do spectral statistics, then you will find Poisson. So however, if you now use all these subspectra and do an ensemble average, then you get agreement with GOE. I mean, it's from the nuclear physics point of view, this is a very good agreement. So it was one of the first nuclei where you found 158 levels, and so here I show the nearest neighbor spacing distribution. A disadvantage of nearest neighbor spacing distribution is that it depends on the binning, that is how large you choose the distances between two spacings. But the advantage is that the integrated nearest neighbor spacing distribution does not depend on binning. So usually one should not only look at the nearest neighbor spacing distribution, but also at the cumulative nearest neighbor spacing distribution, because it does not depend on binning. If you have something like that, you could just change the binning and then to get some good agreement, and then when you change again, you get a bad agreement, so you never know what is now correct. But when you look at the integrated level distribution, then you should get reliable statements or results. And this is the number variance, which should be close to the GOE prediction, and usually when you have a short sequence like 151, it's not that long, then you will see deviations beyond a certain value of L. So here you see space deviations beyond 2 mean spacings. L is counts the number of mean spacings because you unfold. And then here in this case, you find already some deviations below, and at some point you see saturation. And this has to do with the shortest periodic orbit and with the length of your spectrum. And this is a ratio distribution. So the ratio distribution does not depend on unfolding. I mean, to get these results, I had to unfold. I had to use an empirical formula, and I was not sure whether it's now a good one. I mean, when you look at n-flux, then you see it seems to be good. But you can also choose another procedure of unfolding, and then you will get completely different results. So it's really, one has to make sure that one uses the correct unfolding, because if you don't use the correct one, you can distort your results and get results which have nothing to do with your system. But in this case, when you check then the ratio distribution and you don't have any divergences in your spectral density, then this is can be reliable in predictions. I mean, there are also, I'm always a bit careful with ratio distributions because they are insensitive to any small non-universal effects. So now I come back to quantum billiard. So as I said, you have to separate by symmetries. One symmetry is a mirror symmetry. So if you have a billiard with mirror symmetries, like in this case, you have a mirror symmetry with respect to the y-axis and the x-axis. In other cases, you have a symmetry with respect to one axis. Then you have to separate the wave functions into symmetric and antisymmetric ones, because if you have in a quantum system a mirror symmetry, then this means that the wave functions of the corresponding quantum system can be separated into symmetric and antisymmetric with respect to the symmetry axis. Like here you have, here you have antisymmetric, antisymmetric, symmetric, antisymmetric, here antisymmetric, symmetric, or symmetric and antisymmetric. And you can do exactly, here I should just show the results for the rectangular billiard, but for example, for the stadium billiard, I mean, the stadium billiard, it also has a symmetry. So here you have this symmetry and you have this symmetry, and you can do exactly the same with that one. So you can divide into 4 sequences. One would have Dirichlet boundary conditions, the other one Neumann-Neumann, and one Dirichlet-Neumann, and one Neumann-Dirichlet. This would correspond to symmetric, symmetric, antisymmetric, antisymmetric, and so on. So this you can also do. So before you continue with the stadium billiard, I also would separate by symmetry, and then we use, I mean, in this photograph which I showed you, we used a quarter stadium, which means that you have Dirichlet along this boundary. Yeah? Yeah, for this, of course, this is just an example. Usually, you will see overshooting in the nearest neighbor spacing distribution if you don't separate. But I mean, when you have a system with Parsonian statistics, then it doesn't matter. But if you have a chaotic system, then it matters. So that's good that you mentioned. Yeah, I should have mentioned. I mean, I just use this for illustration. So so if you have a mirror symmetry, then you have to separate by mirror symmetries. But you can also have a rotational symmetry, and then it's a bit more complicated. Here I show one example. I mean, this one has a 4-fold rotational symmetry. That is, when you rotate this point here, then you will get exactly the same shape. So it's the shape itself is invariant under rotation by pi/2. And if you have such a system, then you also need to separate by symmetries. If you want to see what you expect to see, like GOE or GUE statistics, as I will show, if you don't do it, then you will see a superposition of Gaussian ensembles. I will show. So now you have to separate by rotational symmetry. Rotational symmetry, first of all, you need to parameterize your billiard area and your billiard boundary. So the boundary, so I use here in this case polar coordinates. So phi is the angle variable, r is the distance from the origin, and now you can define either in the Cartesian, so in the normal coordinate system and vector r, or what we usually do, we define in the complex plane the boundary. So you have then y-axis would be the imaginary axis and x-axis would be the real axis. So then you can define some quantity w, which gives you the points inside the billiard as x plus iy. And on the billiard, you would choose fix r equal to r naught. Then you get the boundary, and there you would get then w of phi equal to x of phi plus y of phi along the boundary. So that's what we usually do. Now m-fold, if you have an m-fold symmetry, here I have a 4-fold symmetry. This means that the boundary follows this law. So if you change now by angle 2 pi over m, then you get back the boundary with such a phase, so w of phi. Then this is equal to this part here times w of phi. You can check by, when you go from here to here, then you will have a change in the real and imaginary part, and this is expressed in terms of this prefactor here. But up to a phase, you will get back your w. And if you do it in Cartesian coordinates, then you get exactly the same. So x of r and phi plus 2 pi over n and y of phi plus 2 pi over m are equal to x of phi and pi of y of phi. So now if you have a system with an m-fold symmetry, then you can separate the eigenfunctions of the corresponding Hamiltonian system also along according to their properties under rotation by 2 pi over m in this example. So that here you have your Schrödinger equation. So this defines you the wave functions and with the Dirichlet boundary conditions along the boundary. And now you can separate these wave functions according to their transformation properties under rotation by 2 pi over m. So for this, you need to define the rotation operator, which is just given by e to the I 2 pi over m times the angular momentum operator, which I call here L. So, and what does it now mean? So classifying the wave function means that if you apply now the rotation operator to the coordinates, then you get the wave function at r and phi minus 2 pi over m times phi. I mean, this you can see by just inserting here the angular momentum operator, and then you see that this is equal to psi ml of r phi minus 2 pi over m times lambda. Now, if you have a rotational symmetry, then this means that you can separate it such that this wave function gives the wave functions at angle phi multiplied with this phase e to the il 2 pi over m lambda. L and lambda take values between 0 and m minus 1. And L defines the transformation class. So if you choose lambda equal to 1, then you can separate your wave functions according to this transformation property. And then, then you will see this has some consequences. I mean, your system as a whole is time reversal invariant. If you look at the complete system, it's time reversal invariant. However, if you now look at the different symmetry classes, what you will find is that when you apply the conjugate, complex conjugation to this wave function, and then you use this relation, then it can be written in this form. So it's equal to the complex conjugate of psi ml multiplied with this phase. And you will have complex eigenfunctions as long as lambda is, L is not equal to 0. When L is equal to 0, then you have a rotational invariant system because nothing changes when you rotate by 2 pi over m times lambda, and then you will have rotational invariance. If your m is an integer number, then you also will have, when you choose here L equal to m over 2, then you again will have here a real phase factor. So you have two wave functions for m integer, you have two wave functions which are real, and all the others are complex. That is, all the other symmetry classes have eigenfunctions which are not invariant under time reversal invariance. And they follow this relation. And this now means that you can show then that the complex conjugate of psi is then exactly given by the wave functions corresponding to the symmetry class m minus L. That is, you can separate your whole system into all wave functions into wave functions which are rotationally invariant, so lambda equal to 0. And if m is an integer, then you have another one which just changes sign when you do the rotation. And you have the rest of all these are complex wave functions, and you have eigenvalues corresponding to states with symmetry class L, and m minus L will have the same eigenvalues. That is, you have degeneracies for, you can separate into singlets. These are rotational invariant ones, which cannot be split into pairs. And you have doublets of same eigenvalues, but transformation properties, symmetry classes are L and m minus L. So in this result you obtain when for non-relativistic quantum billiard. On Friday I will speak about relativistic ones, and there you don't have time reversal invariance, so you don't have this property. This is a property which comes from the fact that the system as a whole is time reversal invariant. Now you can use these transformation properties to separate your states into symmetry classes. I mean, there are different methods to compute the eigenvalues. There's a very famous method by Saraceno and Verchini. Then other methods where you use an ansatz in terms of plane waves, and then you can use the plane waves such that they comply with the symmetry properties. And I use the boundary integral method, and there you can separate from using this boundary integral method. So boundary integral method means that you have to solve such an equation. I mean, this is the phi w prime of phi absolute value. This is just the arc length ds multiplied with some factor q and applied to this wave function u. So, and this q, it's given by I k over 2 cosine of alpha of phi prime minus psi of phi and phi prime times h1, 1 of k rho, where h1 is a Hankel function of order 1. And this boundary integral method, this boundary integral equation, it's derived from Green's theorem. So I won't go into details, but that's how you get this equation. You have to use the boundary conditions and Green's theorem, then you end up with such a boundary integral. And this is used, you can use it as long as you have a billiard with no corners. Then it's a very good method. If you like, in this case, if you can describe the billiard boundary by some conformal transformation, then it's a very good method. So I use it when I have such a situation that I can parameterize the boundary according to this equation. And then, I mean, so what you have to do now, you have to solve this boundary integral equation, and then you get all your eigenvalues. For this, usually what you do, you discretize phi, and then you get a matrix of a certain dimension, depending on how you discretize the angle phi, and then you get essentially an eigenvalue problem in terms of a matrix. And this now can be separated into symmetries by using the m-fold symmetry of your system. So here you have an integral from 0 to 2 pi, and this can be separated now in integrals from 0 to 2 pi over m, then from 2 pi over m to 4 pi over m, and so on. And in the end, you get such an expression depending on the symmetry class. So phi and phi prime now take values between 0 and 2 pi over m. And you get a structure is the same as here. The only difference is that this one is replaced by a term which contains the information on the symmetry properties. So it's a term which has, I mean, these are just, it has these terms here, but you insert now phi plus 2 pi lambda 2 pi over m instead of phi here. And to get the integrand, you have to take a sum over these terms where L determines the symmetry class, and then you get separation into different symmetry classes. And a very nice thing about it is that it's numerically, it's very, very efficient, because now you have to solve, I mean, when you look at the whole system, you will have to define some matrix of some dimension, because which depends on how you discretize 0 to 2 pi. Whereas if you now have here, you only have to integrate up to 2 pi over m, so you can have matrices of much lower dimensions, and you can get many more eigenvalues by using separation into symmetry classes. So for example, here I computed for each, in the example I show, I computed for each symmetry class 5,000 levels, so 20,000 levels in total, and if you use the full matrix, you need several more days than for just for each symmetry class separately. So in here I just show the results that you obtain when you now look at the spectral properties of the symmetry projected eigenstates. Then you have for L equal to 0 and 2, so you have agreement with GOE. Here I show the ratio distribution, so GOE, and for L equal to 1 and 3, I mean 1 and 3 are degenerate. These are the degenerate pairs. There you get agreement with GUE in this case. And here I show also for, I mean, this is L equal to 1 and L equal to 3, so these are the same. And then you have for L equal to 0 and 2, you have the red and green. And then I also look at the spectral properties when you take the whole system, when you take all eigenvalues. Then you can also find a random matrix ensemble. I mean, here I use just GUE, GOE. So depending on the L value, I get either GUE or GOE. And if I take all of them, then you get a superposition of 2 GOE. The 2 GOE comes from the cases L equal to, from these GOE cases here, from red and L equal to 0 and 2. You have 2 GOE. And from the other one, because the eigenvalues are degenerate, you have 1 GUE. So the turquoise curve is 2 GOE plus 1 GUE, and the violet curve is when you take all eigenvalues of your four-fold symmetric system. Yeah, of course, half of them, I mean, 1/4 is missing because they are degenerate, so you don't see them when you do spectral statistics. So, and this, but this has another consequence. I mean, when it was detected like end of 1996. So the Levras, he analyzed spectral properties of a system with threefold symmetry, and he realized that you can, when you separate by symmetry, then you get 1 GOE and GUE. And this is in contradiction to Bohigas, Giannoni, and Schmidt, because they predict that when you have a time reversal system, invariant system, then you should get GOE. So at that time it was quite exciting, and now one knows, I I mean, that's what they found out, that this has to do with the separation into symmetries, because when you separate into symmetries, you will also have complex wave functions. And when you use a combination of these complex wave functions, which you can do because you have a degeneracy, then you would get also real wave functions. So it's no contradiction to Bohigas, Giannoni, and Schmidt, and can be explained by symmetries. So this is one example. I mean, generally, I won't show any examples where you see Poisson or GOE, because this is boring, this is known. I will just show results where you find something which is not according to Bohigas, Giannoni, Schmidt. So this is one example of system with rotational symmetry. There you will find GUE and GOE depending on the symmetry properties. And next example, I know here I just also want to show length spectra. I mean, this is something that Martin will talk about, so I just show them here for the quantum billiard, where I take all levels. So the black one is obtained by taking the eigenvalues for L equal to 0, 1, and 2. And the magenta one is obtained by summing up over the complex valued Fourier transform. I mean, length spectrum, it's a Fourier transform of the fluctuating part of the speckle density. So it's a complex valued function. If you now sum over all four complex valued functions, then you get this magenta length spectrum, which doesn't have peaks below about 3. And the same when you look at the quantum billiard. I mean, it has peaks below 3 here, so this one, but this one, depending on how you sum, you won't find any below 3. And for L equal to 0 and L equal to 2, you have this red and violet one, and then for L equal to 1 and 3, you have, so 1 and 3, I mean, I was now confused. So here I show L equal to 3 and L equal to 1. So you see that they have peaks below 3. Also for the L equal to 0 and L equal to 2, you see that they have peaks below 3. And these are so-called pseudo-orbits. I mean, these are periodic orbits when you look into the fundamental domain corresponding to the symmetry class. And these are no orbits, periodic orbits of the full system. So if you unfold now correctly, then you don't see the pseudo-orbits in the full system. Therefore, they are called pseudo-orbits because they are only visible when you separate by symmetries. And this you can also see here, because here I just skip one symmetry class, then you don't have complete destruction of these orbits, but you only have it when you use the complex valued length spectra. So this is just to illustrate, give one example. I will show more length spectra on Friday when I come to non-relativistic, to relativistic billiards, but just this is what I wanted to show here for this case. And now I come to a second example for a billiard where you don't find what you expect to find. I mean, it's again a billiard with a more or less complete chaotic, I mean, it's more or less fully chaotic. There are some islands. So when you look at the phase space, you see when you start with some trajectory and move it, for example, clockwise. In this case, clockwise, and it will never turn direction. So these are so-called unidirectional billiards. One example is a constant width billiard. It's called constant width billiard because you can put it into a square, and when you then rotate the billiard, it will always touch all four sides. I mean, we have examples in München in the Deutsche Museum. I don't know whether you were to München. There you can see some examples. So you have these billiards, and if you now, they are in a square, and if you rotate them, they will always touch all four sides. And this means they have a constant width. And now this is the Poincare surface of section. I mean, I explained yesterday how you obtain it. I mean, here are the this is length, so the length parameter, I call it, it should be S here, sorry, somehow. So you have your arc length S when you start from some point 0, and then you measure the length up to the point of impact. And then you have the momentum, which is given by sinus theta, where theta is the angle of the trajectory with the interior normal to the boundary. And then when you look at it now, you start in one direction with your trajectory, and it will fill, I mean, for example, that black part. Or if you start with a trajectory which is close to the diameter orbit, then it will always stay in that region, in this turquoise region. If you use a trajectory which is close to the boundary, then you get the so-called whispering gallery modes. So you can separate into a chaotic part, diameter orbit region, the whispering gallery orbit region, and in between we found small islands. And these we only found after computing the Husimi distribution. I will come to it now. I mean, when you do the classical simulations, my student didn't want to believe me that there's an integrable island. I told them, why don't you go there? And they were not able to find it. And then we looked at the quantum system and Husimi distributions, and then we found these small islands. So these are very tiny islands. You see these white holes here in some places, and these are the regions of these small islands. As long as you do not use the initial conditions such that they are within this island, you won't see them. You just see a chaotic sea and then the integrable region around the whispering gallery modes and around the diameter orbit. So this is what it looks like, this chaotic orbit corresponding to this island. And diameter orbit, it's this turquoise one, and whispering gallery modes move very close to the boundary. And so the classical dynamics is unidirectional. That is, you will only fill 1/2 of the Poincare surface of section if you start in one direction, if you don't change direction, if you don't start in the other direction. And so you change from clockwise to anti-clockwise is classically forbidden. However, when you look at the corresponding quantum system, then you will see a transition between both parts. So positive momentum and negative momentum, and this is dynamical tunneling. This is called dynamical tunneling. That's the reason why these billiards are of interest. You know, because here you have the effect of dynamical tunneling, and to this I will come now. I mean, this is what the boundary would look like in this case. It was proposed by Knill in 1998. So this is the boundary shape, and you can choose different values of A3 and A5. A3 must be completely imaginary, and then you can create all kinds of constant width billiards. So, and we did experiments, so I just show here the cavity. It was covered with lead, and it's superconducting, and then we got very sharp resonances, and they have to be sharp because this dynamical tunneling, it becomes visible in small splittings of the resonances of the eigenvalues. So in a circle billiard, you have degenerate eigenvalues. So now when you change the boundary such that it becomes unidirectional, then you will have a small splitting. So the degeneracy will be slightly so open. So like here, for example, here you have a nearly degenerate resonances. Here you have two, and they are only distinguishable when you do these superconducting experiments with, we had exceptionally high quality factors of 10 to 6, so we were able to find in experiments also all eigenvalues. I mean, I did it numerically using this boundary integral method, also using the method of Saraceno and Melchini, and there we did it experimentally. So you will have singlets, like in the threefold case, you can separate into singlets and doublets. Singlets is a diameter orbit. I mean, diameter orbit, there you don't see any transition from plus to minus, so the diameter orbit is exceptional. There you, it will always bounce back and forth between opposite sides. So that's a diameter orbit. It doesn't feel whether the system is unidirectional or not. So, and it will, in the quantum spectrum, it's visible as a singlet. And then you have a sequence of doublets. All the rest are doublets, so nearly degenerate eigenvalues. And so you can separate into singlets and doublets, and then then you can look at the spectral statistics. And to look at the spectral statistics, one first needs to extract these orbits. This is very simple because these are obtained when you diagonalize a circle. Then these are exactly the same eigenvalues except for small deviations. So you can extract them. I mean, in this spectrum, we had about 1,000 eigenvalues and about 10 singlets. And the rest can be split into 2 independent spectra. So you can easily do it. You don't see it in the, when you look at the unfold and look at the n-flux, then it will be a perfect n-flux. This means that the doublets are not coupled to each other. So they don't care about the other partner, whether it's missing or whether it's there. So you can separate them. And here I just show some examples for wave function. This is a wave function corresponding to the diameter orbit. And this can be seen when one looks at the Husimi distribution. I mean, Husimi distribution is obtained by integrating along the boundary the normal derivative of the wave function multiplied with some coherent state. So this is what you do to get a Husimi distribution, and it was shown by Arndt Becker. He introduced it, and he showed that you can interpret it as a quantum Poincare surface of section. And this becomes clear when you look at this figure. I mean, here I have a diameter orbit, and indeed it's, I mean, it's located around the diameter, around p equal to 0. And this you can also see here when you just integrate in this direction, then you get one sharp peak around p equal to 0 and nothing else. So this is what you expect if you have a diameter orbit. And you also have orbits which are close to the diameter orbit in these turquoise regions. And these are nearly, these are very close lying pairs of eigenvalues which correspond to something which looks close to a diameter orbit. When you look here at the Husimi distribution, here you have some which are symmetric around p equal to 0, but the distribution is broader than for a diameter orbit. This is a diameter orbit. Or you can have nearly degenerate pairs of eigenvalues which correspond to close to diameter orbits. This close to diameter orbit means that in the Husimi distributions, they are very close to the p equal to 0. And they are split into 2 peaks. So you have in the island, in this turquoise island around the diameter orbit, you find something like these two. So one is a symmetric diameter orbit, and the other antisymmetric diameter orbit pairs. Or you also find whispering gallery modes. Whispering gallery modes in the quantum system correspond to wave functions which are well localized close to the boundary. And when you look at the Husimi distribution, then you can see that they have a value of momentum which is close to plus or minus 1. So that's another thing which I also can show here. I mean, here you would, when you have a unidirectional system, then you would expect that only p larger than 0 is there's something non-vanishing. However, as you can see here, this is not the case in a quantum system. This is a dynamical tunneling. So you cannot separate into positive and negative parts of the Husimi functions. You always excite p larger than 0 and p less than 0. Like in the whispering gallery modes, you have a peak around minus 0.7 and plus 0.7 in this example. Here I show wave function, a pair of doublets, doublet pair, so which are localized along this chaotic island. So and they also have highest intensity in the on exactly close to these islands of integrable dynamics. This you can see when you compare here. So here I just show the locations of the small islands in the Poincare surface of section. In the classical one, this is a quantum one, and these are peaked exactly around these small islands. Or when you look at the Husimi functions, then you see maxima which correspond to the positions of the islands. So that's how we detected them, by looking at Husimi functions. I mean, this is not a very clear one, but we looked at them and then we found small islands in the classical Poincare surface of section. So another thing that was interesting there, I mean, you have dynamical tunneling. You know that dynamical tunneling leads to splitting of eigenvalues. And now we compared different wave functions. Some are localized around the boundary, others around the diameter orbit, and this one is localized along the diameter orbit and along the along the boundary, and these have an exceptionally high splittings. So these correspond exactly to orbits which are, have a strong dynamical tunneling. The tunneling always takes place via the diameter orbit, so via this part, and this can be seen from the fact that the splittings are largest for whose Hemi functions that have a peak around 0. So that's, this shows that indeed the diameter orbit region is responsible for dynamical tunneling. So you have, if you have a wave functions for p larger than 0, then it can tunnel to p less than 0 via the diameter part, the region around the diameter. So we also, I mean, you have these small islands, you have the Whispering-Gallery modes, you have the diameter orbit, these are all integrable contributions, therefore you don't expect something which is close to what you expect for a chaotic system, but you see it's very close, but it's not close to GOE as you would expect for a time reversal invariant system, but it's close to GUE. And this has to do with this unidirectionality. So you find very good agreement with GUE. This is a GOE curve, this is a theoretical curve for GUE, and you find something, here's the nearest neighbor spacing distributions. When you look now at the RMT model, we have an RMT model which describes the coupling of the chaotic part to the diameter part with two coupling parameters to describe the mixing of the dynamics. And then you find something which is close to GOE if you consider this coupling, this non-zero, this non-integrable part of the Poincare surface of section. You can also, so this is not so important because I don't have much time left, or maybe, yeah, maybe I can just show. I mean, when you, I mean, we were also interested in splitting distributions when we did these experiments, or also people were interested in the splitting distributions because the splitting distribution gives you information on dynamical tunneling. Now here I plotted the splitting weighted density of states. So you have your splittings divided by the average splitting minus 1 times delta of k minus kn. So this is a density of states, and this is the weight of the density of states. And when you plot it, you get something like that. When you fold it with a Gaussian, then you see that you get oscillations, repeating oscillations. And these, so you get a periodic recurrence of large splittings. And this can be interpreted in terms of dynamical tunneling. When you take the Fourier transform, then you see, especially when you look at, when you take a Fourier transform of that one, then you see that they are peaked about one value, and this is exactly the diameter orbit. And this tells us again that the dynamical tunneling takes place via the diameter orbit. So another thing is splitting distributions that were also investigated, and we checked them using our experimental data and numerical data, and then you can derive an analytic expression for the splitting distribution, which is given by that one. So this is, I mean, this was predicted by Lev-Ras and Ulmo in 1996, and we now compare to their results, and we also find an expression which exactly corresponds to their prediction for tunneling. So this is just what else you can do with your system, not only look at spectral properties, but in this case we also looked at the splitting distributions and properties of the tunneling in terms of splittings. So not just spectral statistics. So and here are some more examples. I mean, usually you don't have something between GOE and GUE or Poisson and G, or completely chaotic, completely integrable, but you have something in between. I mean, this is what Thomas Gur mentioned at the end of his lecture yesterday. You can also have something that has chaotic part and integrable part, and then you are somewhere in between. So he introduced a random matrix ensemble, which is a Rosenzweig-Porter ensemble. This one was also derived in times of nuclear physics, so a long time ago, because when you have a nucleus, you usually don't see pure GOE, but you see something which looks like something in between integrable and chaotic. And the same you can have in when you look at a quantum billiard. I mean, here again shows a Limassol family for different parameters. So here you see big islands of integrable dynamics, and when with increasing parameter, the size of these islands decreases, and at lambda around 0.3, you have full quantum chaos. I mean, full chaos. I mean, usually you still have some very small islands, and these would become visible in deviations from of the spectral properties from what you get for a chaotic system. Here I just show the nearest neighbor spacing distribution. So this one is close to Poisson. This moves away from Poisson. And here you see something which looks very close to GOE. These were experimental data, and we had like a few hundreds of eigenvalues only, not several thousands. And here again, you have something which is close to Poisson. You always see the saturation when you have a small number of eigenvalues, and then this approaches GOE when you increase the parameter lambda. And here we have something which is very close to GOE, but you will always find deviations which have to do with the shortest periodic orbit, and also with the length of your spectrum. And also the stadium billiard. I mean, stadium billiard is known as the example of a fully chaotic system, but as I mentioned already yesterday, they have contributions from integrable orbits, and these are the bouncing ball orbits, which are of measure 0. When you look into the Poincare surface of section, you won't see them, because there is just one point. I mean, you have P is equal to theta is equal to 0, and here you have just 2 points in the Poincare surface of section corresponding to this S parameter value and that one, and nothing else. So you won't see it in the chaotic sea, because the chaotic sea consists of many points, and this will be one of all these points. But when you look at the quantum system, then you see them. I mean, here I show the fluctuating part of the spectral density. It was obtained from 1,600 eigenvalues, which were measured in these experiments with a quarter stadium billiard resonator. And when you look carefully, then you see that it has slow oscillations, this red curve here. And this is exactly comes from these bouncing ball orbits. And Martin Sieber, he derived an analytic expression for it. So you can now use this analytic expression and unfold, not in the conventional way, but by adding these small, slow oscillations. So when you unfold according to the conventional rules, then you would get here clear deviations of the delta 3 statistics from GOE. So you can see what kind of effect these orbits, which are measure 0 and the classical limit, can have on the quantum dynamics. So these are scarce, and they can have, I mean, in the nearest neighbor spacing distribution, you don't see much, but when you look at long-range correlations, you see really big effects. Therefore, it's always important not to look only at short-range correlations, but also to look at long-range correlations, because such effects you only will see when you look at long-range correlations. Now, if you unfold by using the oscillating, so you have a slowly varying part, this is a smooth part, plus another part which very slowly as compared to the fluctuating part, then you get good agreement with the GOE prediction. But there you have to take into account the slow oscillations. So one way to get rid of these bouncing ball orbits is to use this tilted stadium. I mean, we did some experiments at room temperature, and there, when you look at them, I mean, it doesn't look perfect, because I had, I don't know, I think 100 eigenfrequencies, and then you get something which looks very close to GOE. But you, of course, have problems with statistical relevance in that case. But this is one way to avoid bouncing ball orbits, to get something which is fully chaotic. So now I will just, in the last half an hour, I will just explain, introduce quantum graphs. This is another type of system which is used to study quantum chaos using systems. I mean, it's a very simple system. It consists of vertices that are connected by bonds. I mean, this can be interpreted like wires, and in one-dimensional wires. And in these wires, you have the Schrödinger equation, one-dimensional Schrödinger equation. So it's given by a wave, one-dimensional waves going back and forth. And you have coefficients, and these coefficients are determined by a scattering matrix, which gives a prescription on how the wave function continues when reaching one of those vertices. So it can be scattered into the other bonds, and here these are two other bonds, or it can be scattered back, and this is described by some so-called vertex scattering matrix. So, and it's a simple system because it's a one-dimensional system. You can, I mean, it's one-dimensional, but you can produce wave chaotic dynamics because these are, they are the effect of the scattering at these vertices is relevant. So the waves on the bonds, I mean, they can be either time reversal invariant. So time reversal invariant would mean that you have here a 0 instead of Aij, and then you have the one-dimensional Schrödinger equation. If you want to induce time reversal invariance violations, then you can introduce a magnetic vector potential Aij, where the real part of Aij is not equal to 0, and Aij should be anti-symmetric. So, and then you can obtain a quantum graph which has the properties of a time reversal non-invariant system. And to get a chaotic dynamics, one has to use all lengths. All the lengths of the bonds should be in incommensurate numbers. Then you can show that then the wave dynamics will be chaotic. And the effect comes from the interference at these vertices. So there you will have phase relations which are either destructive or constructive, and when you choose the lengths incommensurate to each other, then the phases of wave functions entering here will be different, will differ, so there won't be just a multiple of the other waves phases, and then you can produce wave chaos. And therefore, graphs are used also as a model system to study aspects of quantum chaos. And they can also be realized experimentally with microwave networks. I mean, I won't speak about that. Microwave networks, so you simply take coax cables, connect them at joints. I mean, you have commercial T joints, so then you would have connectivity 3, like in this example here. Or you can also produce other joints with higher connectivity. But these need to be then constructed such that they comply with the scattering matrix of the corresponding quantum graph. So the characteristics of the quantum graph is defined via the connectivity. That is, you can have more than 3 bonds meeting at a vertex, and the connectivity matrix, it's equal to 1 if vertices I and j are connected, and it is 0 otherwise. So this defines the connectivity matrix. And you have several requirements. One is the continuity. That is, when a wave function arrives at a vertex I, it will take some value phi I. And this value should be the same for any wave entering a vertex I. So when the wave enters from vertex j to I, it should be the same as for a wave entering from another vertex. So that's a continuity condition. So, and also, I mean, at 0 you have a phi I, at Lij, at another vertex you can have a phi j. So these can have different values, but the values at each vertex at a vertex should be the same for all wave functions entering that vertex. Then you have another condition, that's a current conservation, that is the flux coming into a vertex plus the sum going up plus the flux going out. It should be equal to some lambda I times phi I. Lambda I defines the boundary conditions. So these are the 2 requirements. And now you can derive analytical from these requirements. You can derive the vertex S matrix using these properties. So lambda I is given by these little lambda I divided by the valency of a vertex, so the number of bonds that are connected at vertex I, and multiplied with the wave number k. And then this is then so it only depends on this valency of the vertex I and on this lambda I divided by k, so on the boundary conditions. So there are, you have different boundary conditions. One boundary conditions would be Dirichlet boundary condition, which would mean that you choose here lambda I to infinity. And this would correspond to a quantum graph which consists of separate bonds. So there's no coupling between bonds. So, and each of them has a different length, incommensurate length, and then what you would obtain is just Poisson in that case. So this is of no interest this case, because this is then all bonds are not connected. Usually, when we are more interested in Neumann boundary conditions, because such graphs can be realized experimentally very easily using coax cables and commercial joints. And this corresponds to lambda I equal to 0 here. And then you can show that then you will get the results of the Gaussian ensembles, depending on whether you turn on a magnetic field or not. And the vertex matrix then is very simple. It's just given by 2 divided by the valency of vertex I minus delta jj prime. So it's a very simple scattering matrix which does not depend on k. So these 2 boundary conditions are the only ones where the vertex scattering matrix doesn't depend on k. So that's also important, because then in experiments we don't need to worry about the frequency range where we look at, because the scattering matrix has everywhere the same properties. So you can analytically solve these equations. Because you have a wave function on bond ij, so you can make a general ansatz which fulfills the continuity properties. Because when you see here, when you insert here a 0, then you get here sinus k Lij divided by sinus k Lij multiplied with Z1. And here you then would get a 0. So then you get that it's equal to phi I multiplied with this phase. And this phase will also cancel out. Where is it? Yeah, here you have it. For x equal to 0 at 0, and when you have x equal to Lij, then this part vanishes, and this part, then the phase will cancel again with this one, and here you will have sinus k Lij divided by sinus k Lij, so then it will be equal to phi j. So it fulfills the continuity conditions. And now to fulfill the current conservation, one just inserts this expression into this equation here, the Z1, and then one can derive a matrix which I call here H hat of K. So it's similar to a Hamiltonian. So it's given in this form. It's it has a very simple structure, because entries are just cosine functions and sine functions. And you essentially have to solve this eigenvalue problem. And it has solutions for values of k for which the determinant, here this determinant is equal to 0. So you can get the eigenvalues of a quantum graph quite easily by solving this equation. And when you have your values of k, then you can get the values of the wave functions by using this expression essentially. So you can numerically obtain eigenvalues and wave functions of a quantum graph. So that's another nice property. It's much simpler than for a quantum billiard, where you have to find the zeros of complicated functions, which can have problems depending on whether you have corners, whether your billiard has a corner or not a corner, and this is much simpler here in this case. Therefore, it's also used a lot, but it has drawbacks, as I will show now. Another nice thing about quantum graphs is that average integrated spectral density is proportional to k. That is the spectral, then the integrated one is proportional to k, and this means that the spectral density is a constant. So unfolding in this case is very simple. You only have to multiply, you add eigenvalues with this constant here, and then you can then they are unfolded. So it's very simple. This is L tot is the total length of your graph. Sorry, yeah, good that you asked.
So the connectivity matrix is inside that L total.
Yeah, this one, these are the lengths of the bonds, Lij, and when you sum over all lengths, then you get your L tot.
Okay, and why is the physical reason why like the stabilization is linearly for all?
I think you have to use micro. Sorry, I forgot. Because maybe there are Zoom members who...
Yeah, I was wondering about what is the physical reason about why the density of states, the smooth part, grow only linear without regarding the connectivity matrix, because we'll expect that if we increase the connectivity, for example, of making all the C's equal to 1,
yeah,
there are more states, and that can be like increase. I would thought that it will increase like at least not linear if the connectivity increase.
This is, I mean, it's a one-dimensional system, and you can show that it only depends on the length, because the waves are all one-dimensional waves that move along all these different bonds, and the total length then gives you essentially the number of eigenvalues. So when you have, for example, when you have one length, then you can compute eigenvalues explicitly, and so this is similar.
Okay, I get it, I get it. Yeah.
Okay. So we have to remember to use it maybe. So where were, okay, so it's very simple to, I mean, you only have to compute the total length of your graph, and then you can unfold easily. So, and there you can also use it, I mean, I'm not talking about open scattering systems. I mean, you also have quantum chaos. You can look at quantum chaotic scattering. This is quite complex. But this can also be, a scattering matrix can also be realized with quantum graphs. I mean, when you have a microwave billiard, you have a scattering system because you have two antennas attached to a microwave billiard, and you send something in and you get something out. That is, there you naturally have a scattering system. And this we use to investigate properties of quantum chaotic scattering. But I won't talk about it. And another, here you can also use a quantum graph to get an open scattering system by just attaching leads which go to infinity in a sense. So you have no more vertices. You just have a plane wave which goes out forever if it goes out, or it comes in from infinity. So you can send in a plane wave at a vertex, and then you can let it move around, and at some point it will either go out at another lead or at the same lead. So you have a scattering system. And for the scattering system, you can also derive explicit expressions for the scattering matrix. Here I just give one example. There are different ways to define it, and here I just define the scattering matrix when you have m leads attached to a quantum graph which consists of v vertices, then you will have an m times m scattering matrix, which can be written in this form. And this has exactly the same form as the scattering matrix of quantum chaotic scattering, which you would get when you do random matrix theory. I mean, it's Werber, Scott, Weinmüller, and Zirnbauer, the so-called Heidelberg approach, about which I won't speak, but it has exactly the same form as that scattering matrix of quantum chaotic scattering random matrix theory. So then, I mean, this matrix W, it describes the coupling of the M leads to the interior modes, essentially. And time reversal invariance would then mean you have a unitary matrix, so there time reversal invariance means that the inverse, the time reverted scattering matrix is equal to the Hermitian conjugate of the scattering matrix. So this would mean time reversal invariance in a scattering matrix, a system where the scattering matrix is a unitary matrix, just to mention. So there you would see, yeah, so that's what you then get. And there are also, for these quantum graphs, you can derive an exact semi-classical, it's not an approximation, an exact semi-classical expression for the trace formula of the fluctuating part of the spectral density. is given again in terms of a sum over periodic orbits of length LP. This would correspond to the Maslow index, which you can compute explicitly, and then this would correspond to the stability amplitude, which is given in this form here. So the Vs are the verticities, and mu p, this is not this one, but this mu p is the number of vertices where you don't have backscattering. So this is, I just want to mention it because this is very practical, as I will show to you now. I mean, first of all, I show to you now for the results for a GOE graph, so a graph with time reversal invariance, and all lengths are incommensurate, so you have a chaotic system. And then you look at the spectral properties, you see nice agreement as long as you only look at short-range correlations. However, when you look at long-range correlations, then you see deviations which remain independently on how many eigenvalues you use. And this is one of the drawbacks of these quantum graphs, that there you can have backscattering. But as I will show now, I mean, here I show in red the fluctuating part of the spectral density. In blue, I just show what you would get when you average over it. Then you get slow oscillations. And these slow oscillations, to understand them, we use the Fourier transform of the spectrum. Then you get length spectra, and then you can identify lengths. And we showed that these are exactly correspond to backscattering. So when you have a quantum graph with Neumann boundary condition, you also have the possibility that a wave just jumps back and forth between vertices I and j. And these, of course, are waves that don't see whether your quantum graph is chaotic or integrable. They don't care about the rest. They don't see the rest. So, and these, of course, will lead to deviations from what you would expect for a typical chaotic system. So that's one of the drawbacks. You can also try to define other kinds of boundary conditions, but essentially you always have to fight with such deviations from perfect quantum chaotic behavior. And to see this, we looked at the exact semi-classical expression for these orbits. So from all the possible orbits, we just use from the semi-classical trace formula those orbits which correspond to this backscattering. We look at the Fourier transform, compare it to the Fourier transform, and also here just compare fluctuating part of the eigenvalues with what you obtain when you use this trace formula. You integrate it over k, and then you see that this green curve, corresponds very well to what I showed to you before, to the slow oscillations. So and this tells us that indeed the deviations are due to these orbits scattering back and forth, and this also becomes clear when you look at length spectra. I mean, I take the Fourier transform of this trace formula and the Fourier transform of the spectral density, which are obtained from numerical results, and then you can see that the peaks of the semi-classical expression agree very well with the length of the bonds. So all these peaks are at the length of one of the bonds that constitute the quantum graph. So that's a real drawback of quantum graphs. You always have to deal with such backscattering properties. And to get rid of it, one possibility is to define the vertices so the vertex scattering matrix in such a way that backscattering is not allowed. So there are some approaches which try to use that one, but then you have another problem, because if you forbid backscattering, then you will have lack of complexity. Then you will see deviations from what you expect for a typical chaotic system, because simply you have a reduction of the complexity of your wave dynamics. So the complexity really depends on how the waves entering a vertex couple to each other, so the phases of them. And if you now forbid going back, then you will have a lack of chaoticity. So now I come back as another nice thing about these quantum graphs is that you indeed can realize a system with symplectic symmetry. That was one of the reasons why we started looking at quantum graphs. So just to remind you, I mean, yesterday we heard about the threefold Dyson's way. So you have either Hamiltonian systems which are invariant under unitary transformations. These are Hermitian Hamiltonians, complex Hermitians, which correspond to systems with violated time reversal invariance. You can have Hamiltonians, which are time reversal invariant, and these are symmetric Hamiltonians, and you can have the third class of systems, universality class, would be the symplectic symmetry, and this becomes of relevance when you have a spin 1/2 system, which is corresponding to a time reversal invariant Hamiltonian, which doesn't have any additional rotational symmetries. Then it will have the structure, will be symplectic, as I told you yesterday. I mean, the time reversal invariance operator of a spin 1/2 system is given by the product of complex conjugation and the symplectic unit matrix. And you can show that the Hamiltonian, when it's time reversal invariant and it's Hermitian, then you find that the Hamiltonian of a spin 1/2 system with time reversal invariance will be symplectic. So therefore, it belongs to the symplectic group. And then from this, you can show that it's quaternion real, but I don't go into details. I mean, you can write it down in a quaternion basis, which is built up by the states 1 to n. So you have a 2 n-dimensional system. You can separate it into n states, 1 to 3 and then n states, which you obtain from these states by applying with the time reversal operator, and because these are orthogonal to each other. So that's one of the properties of systems with symplectic symmetry. So there you have Cramer's degeneracy, you have pairs of degenerate eigenvalues. And the general structure of such a Hamiltonian is of this form. So you have here a Hermitian matrix. Here you have the complex conjugate of the Hermitian matrix. Here you have a potential, so that couples H0 and H0 star. And here this is minus V star. So that's a structure, and this is exactly what was done in the realization of quantum graphs. They just mapped such a Hamiltonian onto a graph system. So this graph system, it consists of 2 graphs. So one graph with a non-zero potential which is equal to pi over 2, and an identical one. This vertex corresponds to this vertex corresponds to that one, this to that one, and this to that one. So you have 2 identical copies. The only difference is that this one has a phase pi over 2, this one has a phase minus pi over 2. So when you write it down in terms of the matrix H, then you will have a complex conjugate. So one is H0. So this, for example, would then correspond to H0. This would correspond to H0 star. And they are coupled at bonds. So these are not corresponding vertices, but this vertex corresponds to that one, this to that one. So you couple them by one bond. And you have a relative phase of pi between these bonds. So these bonds would correspond to the matrix V. For example, this bond would correspond to the matrix V, and this bond would correspond to the matrix minus V star, where V is, in this case, would be a real potential. So that's how the GSE graphs are realized. I mean, this was Martin Sieber and Joyner. They wrote a theoretical paper on how to realize them, and then together with the group of Stöckmann, they realized an experimental quantum graph by using exactly this prescription. And so these are the things one has to take into account. First of all, these phases must be plus or minus pi, and then you have to make sure that the relative phase between these bonds is pi. So this can also be realized experimentally. So we did experiments, but here I just show numerical results. Here for the GUE graph, which would correspond to H0 in the graph, and for the coupled one, which is a GSE graph. So in both cases, you find very good agreement when you look at short-range correlations. But when you look at long-range correlations, then you see, again, these deviations, which can be attributed to backscattering. I mean, to see this, you just take the Fourier transform of the spectral density, and then in the length spectra you see peaks at lengths which correspond to one bond length. So also in these cases you have to deal with backscattering, and it's especially large in the case of GSE graphs. So just before ending, I will show one way how you can get rid of these backscattering. This can be done by looking not at one graph, but by looking at the level dynamics. So you take your, you take your graph like this. For example, you have such a graph. Here you have another one. And now you vary the length of one of them. So when you vary one length, so you take L, which depends on a parameter mu, and vary it slowly, then you can produce a whole dynamics. So this would be a parametric realization of a graph. So you change the length of orbits, and now this would be this parameter lambda, so this would be here lambda instead of a mu. And if you vary it, and now for each length you determine the eigenvalue, so one length would correspond to what you saw before, so one spectrum for one graph, and now you change the parameter, compute again the eigenvalues, and then you get, in the end, you get a so-called level dynamics. For the GUE graph, it looks different from what you get for a GSE graph, and what is even more important, you see in both, you see these straight lines of something that doesn't really change. I mean, when you change the length of a bond, then you will change the spectral density. That is, you will change the number of eigenvalues. Therefore, you have something which moves up here. But these are exactly, these correspond to eigenvalues that correspond to this backscattering. And now to get rid of them, you can just cut out this part here and look at parametric correlations. I mean, you cannot look at one fixed value of lambda. If you cut out this, then you will have missing levels in your sequence, and then you will see deviations from what you would expect for GOE or GSE or GUE. However, if you now take parametric correlations, so you cut it out and then look at properties between different lambda values, like for example, here's the curvature distribution. Curvature distribution is obtained by just computing the curvatures for each of these spaghettis. So these are all spaghettis. You can compute in each point the curvature, and then you can look at the distribution of curvatures, which does not depend on whether you have all eigenvalues or only just a part of it. That's a nice thing about these statistical properties. Then if you do not extract the non-universal contributions, then you would get this black one was experiment, red one was numerics for GUE and GSE. And now if you extract non-universal contributions, then you get a very good agreement with randomatic theory predictions. So this would be one way to get rid of these non-universal contributions. But it's a very, from the experimental point of view, it's quite complicated, the experiments. And here I just show another one is the so-called avoided crossings distribution. To get it, you have to look at cases where you have some spaghettis which come very close to each other and then go apart again. This is called avoided crossings, and then you can look at the distances at these avoided crossings, and then you can get these distributions. There are randomatic theory predictions, analytical results, and we compare just to the analytical results here for the GUE case and for the GSE case. So this is another way to study properties of a quantum system. If you have a system which depends on a parameter, then you have a large other statistical measures to look at to see how whether the classical dynamics is regular or chaotic or something in between. So for that, these quantities are quite useful. So this was it. So thank you for your attention. So if you have now questions, then I come with a phone. Okay. Not with a phone, but with a microphone.
Thank you for your talk. I want to ask you if you have a distribution that it looks like something in between, for example, GUE and GSA.
Yeah.
Can you is there a procedure to separate what part is of some distribution and what part is from another distribution?
This usually not.
No.
But for these cases, you have even analytic results for the so-called transition ensembles. So then I would compare to these predictions from random-matrix theory. So there's, I mean, you have these from between GOE, GUE, you have analytic results, or GOE to GSE, and then you can compare to these. So you don't really need to separate. I mean, it depends on how much you know about the origin of these properties. Then sometimes it's possible to extract, but usually you don't need to, really.
Okay.
Thank you for the lecture. Can you go to slide 10, please? Can you go to slide 10, please? The 10th slide.
Number?
10. That's slide 10. There's a plot that
10.
I'd like to...
Far away, yeah.
To this. Yeah, it's a plot on the correlations for sigma squared that, like, it deviates...
this one?
The previous one, please.
A previous one.
Yes,
yes.
Yeah. The sigma square, there's these deviations in the end that you explained, but I couldn't understand.
So usually, I mean, in this case, the reason, I mean, if you see deviations, then there are two reasons. One reason is that if you have short sequences, a number of eigenvalues, then you usually, I mean, in Lookyer data, you always see deviations starting from 2 to 3. But there can also be another reason. I mean, even if you have 1,000 eigenvalues, you will see saturation at some point, and this value of L depends on the length of the shortest periodic orbit. Because the shortest periodic orbit, it's a non-universal property in a sense. So when, I mean, I didn't show, I showed you one figure. There was a fourfold case. Oh no, I have to go back because I can explain. There. Here you have short periodic orbits, this yellow one and the green one. And these can lead to the deviations from what you expect for GOE or GUE, and you can extract them. I mean, you have to extract them if you want to see perfect. This you can see a bit. I mean, I didn't say it here. Here you see some deviations, and these are exactly due to these short periodic orbits. But I have a method to extract them, and then by just your Fourier transform, and then you cut out the peaks that correspond to these lengths, and then it's similar to extracting bouncing ball orbits in a stadium billiard. So you can extract them, and then you will see a perfect agreement with GOE.
Okay, thank you.
So more questions then?
Well, good morning, everyone. My question is about the constant with billiards.
Yeah.
The unusual GUE behavior of the spectrum is just with the mixed classical phase space, or there is some reason?
No, it has to do with I mean, you cannot, when you have a quantum system, I mean, a quantum billiard with constant width, you cannot separate both directions. So, I mean, due to tunneling, you get this dynamical tunneling, you get a superposition of both cases, and this then will be like in the threefold or fourfold case where you have a separation into two complex wave functions. You have exactly the same in the unidirectional case, that you will have complex wave functions, and but it's not a contradiction to time reversal invariance, because you can use a combination of them and then you would get a real wave function. So exactly the same argument, essentially. So in this case, you have one which rotates in this direction, the other in the other one, and then, yeah.
Yes, but some billiard systems present the mixed classical phase space, but with the invariance for reversal by the operator.
I don't understand.
Some classical billiards presents the mixed classical phase space, but remaining the invariance by a reversal temporal. And the behavior of the spectrum properties is not GUE, neither GOE, some intermediate between.
You mean for this case here?
No, not for the constant width billiard, but for other billiards.
You mean now, yeah. This you can have, it's called then partial time reversal invariance violation. I mean, this case, we simulate even in experiments. Okay. So we have, when you put a ferrite, magnetize it from outside into a microwave cavity, then you get something which is between GOE and GUE, so partial time reversal invariance violation. And for this case, there are also analytic results.
Okay.
So this is called partial time reversal invariance violation then.
Okay, thank you.
Thank you. It's about the Bunimovic scar.
Yeah.
I think it's 29 slide.
Bunimovic was at the end, I think. This one?
Yeah, this solution is for a quarter of the stadium or the full?
This one?
The equation. Yeah, is the solution for this quarter or for the full stadium?
Yes.
For the
no,
full?
for the quarter stadium, quarter.
Yeah.
So it's with the one I choose, anti-symmetric one. So then you have Dirichlet, and Dirichlet.
Oh, okay. So I can obtain the full scar using just this quarter. Yeah.
What you can do, I mean, that again, it's from the numerical point of view, it's also very important just to separate by the 4 symmetry classes and then compute for each of them separately. Okay. Then in the end, of course, you can put them all together and then you have the full spectrum. But in that case, you would see not 1 GOE, but 4 GOE. Oh, because you have a superposition of 4 GOE in that case.
Yeah, okay. That's it. Thanks.
And the problem is when you the more GOEs you overlap, the more closer you will be to Poisson. Yeah. So you won't see any GOE behavior anymore if you have too many symmetry classes on top of each other.
Yeah. Okay, thanks.
Barbara, you spoke that the unidirectional billiard predicts the GUE distribution.
Yeah.
Because of the trajectories?
Yeah, unidirectional properties.
And when you look for the C3 or C4 billiard, it's possible to see something similar just looking to the phase space or trajectories?
Yeah, I mean, I never looked at it from the classical point of view. You have to see something, because you have. I mean, for the threefold, for example, you can separate into rotationally invariant and then into one rotating in that direction, the other one in the end rotating in the other direction, because this has to do with the symmetry properties, and these you also have in your classical system.
Okay. Okay. Thank you.
Yeah.
More questions?
More questions or no? Okay, I can get it. So now we can have a break and start again at 11:30. Thank you.